Hello everyone. In this video, I am going to discuss the remaining solutions of data science and semester paper. Let's begin. I had already discussed the first question with its A part, its B part, the second question with its A part and its B part. I had also discussed the third question with its A part and B part. Let's begin with the fourth question. The fourth question is asking to explain any four common feature engineering techniques for continuous or categorical data. I have given some of the common techniques, engineering techniques for continuous data, like the raw measures. Raw measures refers to those data that hasn't been transformed yet. Rounding. Rounding refers to the process of rounding a value to the nearest integer or decimal, etc. It is necessary because it may lead to noise, so it is better to round off the errors in the data. Scaling. Scaling is of various types like log scaling, z-score scaling, min-max scale, etc. Imputation. Imputation refers to filling the missing values using mean, median, model output of the dataset. Binning. Binning is a process where we transform the numeric features into categorical features like values between a range of 1 to 10 can belong to A, the values between 10 to 20 becomes or belongs to B, etc. Let's move to the next question. So question number 4b is asking what is sampling from a distribution and describe inverse transform sampling or Monte Carlo sampling with an example. So sampling from a distribution means generating random data points that follow the probability distribution's characteristic, such as its mean, variance, and shape to simulate or approximate the real world variability. It is generally important in the terms that if there's a very large data set and we want to perform some operation on the data set, then sampling will help us to perform uh, get a better understanding of the data set. Let's understand the sorry let's understand the Monte Carlo example um, with sampling with a example data set. First of all, our goal is to estimate the probability that a new FIR result in the BNS 80 dowry rate based on the uncertain input. So we will take the step one that we will estimate the feature distribution from the dataset of 50,000 FIRs. Then we will look for some of the important hypothetical values like dowry demand. If yes, then this value P is equal to 0.32. Injury type, if burn, then P is equal to 0.12. If the time system marriage is distribution above, then it can be taken. Victim age is normal, like 26 or 7 will be the range. Gender, if 78% female. Relationship with training data distribution may be taken. In step 2, we will perform Monte Carlo simulation that will work on 10,000 synthetic FIRs. For each simulation, we will first sample the dowry demand from Bernoulli's, then sample the injury type, categorical distribution, then we will sample times marriage using inverse transform sampling, then we will sample the victim age from the normal distribution, then we will feed the sample values into the IPC or BNS classification model, and finally predict the section and count how many times the BNS 80 occurs. This whole process will be followed using the Monte Carlo sampling method. Let's move to the next question, 5th A. It is asking to distinguish between parametric versus non-parametric models and supervised versus unsupervised learning models with example. First, let's discuss parametric models and non-parametric. In terms of assumption, parametric models take strong, linear, or normal assumptions, where non-parametric models make very few or none assumptions. Parameters in a parametric model are fixed number, whereas in non-parametric model, the parameters grows with the data. Parametric models have limited flexibility, whereas non-parametric models have high flexibility that captures more complex patterns. In parametric models, the data needs less training data, whereas in non-parametric model, more data is required. In parametric models, computation is efficient, faster training occurs, whereas in non-parametric models, intensive computation is done and it is slower as compared to the parametric model. The interpretability of parametric models is high, That is, it gives clear parameter meaning. Whereas in non-parametric model, interpretability is quite lower. And examples of parametric model include linear regression, logistic regression, etc. Whereas example of non-parametric models include KNN, decision trees, SVM, etc. Now let's discuss about the differences between supervised and unsupervised learning. The supervised learning data in supervised learning, the data requires labeled data, that is input plus output. Whereas in unsupervised learning, the data is unlabeled. The goal of supervised learning is prediction and or classification, whereas unsupervised learning goal is pattern discovery or grouping of data. Supervised learning evaluation is evaluates with more accuracy, precision on levels is here. Whereas in unsupervised learning, evaluation occurs in an internal manner, like the Shillot score is an example. Supervised learning example include linear regression or SVM classification. Unsupervised learning examples include K-mean clustering, PCA, which is used for dimensionality reduction. Supervised learning use cases are in spam detection, whereas unsupervised learning are used in customer segmentation. Let's move to the next question. In the question number 5th B part, it is asking to define accuracy, precision, recall, F1 score, and illustrate the computation using a confusion matrix. So here, before creating the confusion matrix, let's understand some basic terms. TP refers to the true positive or when model correctly predicts the positive. FP refers to model false positive or when model incorrectly predicts the positive. Fn refers to false negative or when model incorrectly predicts negative. And Tn refers to true negative when model correctly predicts negative. So this is our corresponding confusion matrix. That is, if the actual positive and predicted positive are the same, then true positive occurs. And if actual positive is if the data contains actual positive but the model predicted negative, then it becomes false negative. If the data is actual negative whereas the model predicts a positive, then it will give us false positive. Whereas if the value is actual negative and the model predicts a negative, then it gives us true negative. Similarly, here's a sample example. The value of TP is equal to 80, Fn is equal to 20, FP is equal to 10, and Tn is equal to 90. And we will now calculate accuracy using the formula true positive plus true negative divided by false negative plus false positive plus true negative plus true positive to gain 0.85 as answer. Similarly, precision out of all predicted positive cases, how many were actually positive. It can be calculated using formula TP is equal divided by false positive plus true positive, that is equal to 88.9%. Next, recall or sensitivity. It can be calculated by using the formula T true positive divided by true positive plus false negative, that is will give 80%. F1 score. F1 score refers to harmonic mean of the precision and recall. It is useful for the data set if the data set is imbalanced. F1 is equal to 2 into precision into recall divided by precision plus recall, that will give us 0.8 answer. It is I created a general table for representing these answers, like accuracy 85%, precision 88.9%, recall 80%, and F1 score 84%, where accuracy is the overall correctness, precision is the correctness of positive prediction, recall is the ability to find the actual positive, and F1 score balances of precision and recall. Let's move to the next question. Now question number 6a is asking to describe how the coefficient in linear regression are estimated using either the closed form equation or gradient descent. So in the closed form equation, we follow the given step. First, we compute the value of x transformation sorry transpose of x and x, where x is a matrix, and then we compute the inverse of this transpose of x into x, the inverse. Then we multiply this whole value by the x, the transformation of x matrix into y, and we then directly get the coefficient estimates Its advantage includes that it gives an exact solution. No learning rate is needed for it. Good for small, medium data sets. And disadvantage of this method involves like it requires metric inversion. Let's understand it with a common example. The suppose the data set contains x input values at 1 to 3 and the output values at 2 3 6, and we will add the bias term by first creating a matrix of the inputs and the outputs. So then we will compute the value of the coefficients by using beta is equal to x transpose of x into x whole inverse into transpose of x into y, and we will get our answer as the coefficient is equal to 1.9 and intercept is equal to minus 0.33. Let's move to the next question number 6, the B part, which is asking to explain the logistic regression and use the logistic function to calculate the probability of a class for a given input example. So logistic regression is a classification algorithm which used which is used when the output is binary, that is it predicts either yes or no. If it predicts 0 or 1, only two outputs are possible, then we use logistic regression. It predicts the probability that an input belongs to the positive class, that is p of y is equal to 1 divided by x is equal to p. It's a numerical representation. It does this by computing a linear combination of the features that is represented as z is equal to beta naught plus beta 1 x1 plus beta 2 x2 up to beta n xn. Next, we pass the value of z through the sigmoid or logistic function, which introduces non-linearity into our dataset to convert it into a probability distribution that will give us sigma of z is equal to 1 upon 1 plus e to the power minus z. Then we will calculate the logistic sigmoid function. The sigmoid function converts any real number into value between the range of 0 and 1. That will calculate at p, that is the predicted probability of class 1 is equal to 1 upon 1 plus e to the power minus c. If the value of p is greater than or equal to 0.5, then the predicted class will be 1. And if the value of p is less than p cap is less than 0.5, then it will give the predicted class as 0. Now let's understand it using a common example. Here we have taken some of the model coefficients like of interrupts, dowry demands, marriage years, one injury, and its symbol is beta naught value minus 2.2, and beta 1 for dowry demand and value is 1.5. For marriage years, beta 2 is the symbol and the value is 0.3. One injury symbol is represented using beta 3 and its value is 2.1. Then we will plug in the values and calculate the z value as beta 1 plus beta 1 z1 beta 2 z2 plus beta 3 z3, and we will calculate it by using the input example of a fire case where the dowry demand value is 1 and marriage years is 2 and one injury is 1. Then we will calculate the value c by using this formula. Beta naught minus 2.0 plus beta 1 is equal to 1.5 into x1, sorry z1 is equal to 1 plus beta 2 is equal to 0.3, sorry minus 0.3 into z2, that is 1, and then similarly beta 3 is equal to 2.1 and the value of z2 is equal to 1, and then we will calculate the value of c minus 2.0 plus 1.5 minus zero point 0.6 plus 2.1, which will give us 1 as the answer. Then we will apply the logistic function to this value of z, that p cap is equal to sigma 1.0 is equal to 1 upon 1 plus e to the power minus 1, and we will gain the final answer of sigmoid function as 0.731. So our final prediction will be b of bns 80 divided by x is equal to 0.731. Thank you very much for listening. The remaining questions I will discuss in the part C of this video. Thank you very much.